Okay, so we're going to continue with our discussion of the atmosphere by taking a deeper dive into how clouds are created, how wind is created, and therefore the combination of those two things, how weather happens. So before we get to that, we're going to have to talk about atmospheric moisture, and this could be really complicated, so I want you to make sure that you're taking notes so that we can answer any questions that you have on this material when we meet on Monday. So when we're talking about atmospheric moisture, we're talking about water in the atmosphere in the form of water vapor, which is a gas. Okay, so it's not steam, it's not any of that, it's water vapor, the gas, water vapor. We're going to talk about two important concepts, vapor pressure and relative humidity. Oftentimes people think that a measure of atmospheric moisture, the best measure of atmospheric moisture, is relative humidity. Relative humidity is actually quite complicated, and I don't know why the weather apps always show you relative humidity. I think it's a useless tool for the average human trying to interpret the weather. So we're going to get into that, and why I think it's bad, and why you should ignore it, and why you should instead think mostly about vapor pressure, or sort of an actual quantity of water in the atmosphere rather than a relative humidity. So before we get to that point, let's first start with this very, 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 very important concept, which is that the warmer the atmosphere is, the more water it can hold as water vapor. Okay, so for every 1 degree increase Fahrenheit in temperature, the air can hold 4% more water vapor. Water as a gas, water vapor. Okay, this has important implications for climate change, which we'll get to in a minute, and this slide kind of teases by saying warmer air leads to more evaporation, which leads to more precipitation. So let's take an example. We have a parcel of air at 90 degrees Fahrenheit, and then a couple hundred miles away, let's say we have a parcel of air at 40 degrees Fahrenheit. If the parcel of air that's 90 degrees Fahrenheit is holding the maximum amount of water vapor that it can, it will be containing 30 grams per kilogram of water vapor, meaning for every kilogram of air, it will contain 30 grams of water vapor. That's the maximum amount of water vapor that it can contain. So if it contains the maximum amount of water vapor, then it is considered 100% saturated. Now let's look at the 40 degree parcel of air. Now let's say the 40 degree parcel of air is also 100% saturated with water vapor. It contains as much water vapor as it can possibly hold. Because it is significantly cooler, it can actually only hold 5 grams for every kilogram of air. So assuming these are both 1 kilogram parcels of air, nothing else is different between them except for their temperature, the 90 degrees parcel of air will be able to hold 6 times more water vapor than the 40 degrees parcel of air at maximum. That doesn't mean that the 90 degree parcel of air always has that much water vapor. It just means that it can hold that much water vapor. So this is where we kind of diverge with the idea of relative humidity versus dew point. So let's say we've got that 90 degree parcel of air, okay? At maximum, it can hold 30 grams per kilogram, which means that its saturation vapor pressure, okay, is 30 grams per kilogram. How much water it actually contains, though, is its actual vapor pressure. And if you divide the actual vapor pressure, actually how much water that air contains, divided by the saturation vapor pressure, and you multiply that number times 100, that is the relative humidity. The relative humidity is measuring how saturated a parcel of air actually is. It's not measuring how humid it feels at all. The relative humidity is measuring what percentage of total water vapor that particular parcel of air is holding relative to how much it can hold. Let's take this example here, and then I'm going to explain dew point and why that's a much better thing to use than relative humidity. So let's say all of these parcels of air have a 50% relative humidity, right? That's what RH here stands for, 50% relative humidity. Assuming that the parcel of air is 55 degrees, okay, it's the amount of water that will be contained in that parcel of air, okay, is going to be, water vapor, is going to be significantly less than a parcel that's at 75 degrees with a relative humidity of 50%. And that is going to be significantly less than the water vapor that's contained in a parcel of air that's 95 degrees with 50% relative humidity. So all of these have 50% relative humidity, but because the warmer air can hold more water vapor, 50% of however much it can hold is significantly more than 50% of however much a 55-degree parcel of air can hold. So this is where the idea of dew point comes in. Dew point is the temperature at which the parcel of air, okay, if it's cooled down to that temperature, that parcel of air will achieve 100% relative humidity. So for a 55-degree parcel of air with 50% relative humidity, the dew point is 37 degrees Fahrenheit, which means that if I take this parcel of air and I cool it down to 37 degrees Fahrenheit, it is going to be 100% saturated. It's going to contain as much water vapor as it possibly can hold. Now, a parcel of air that's 95 degrees with a relative humidity of 50% has a dew point of 74 degrees, which means that I need to cool this parcel of air down to 74 degrees to achieve 100% saturation, 100% relative humidity. You'll notice there's a big discrepancy between this 37 degrees and this 74 degrees. For this parcel of air, I have to cool it down all the way to 37 degrees Fahrenheit in order to achieve 100% relative humidity. For this one, though, even though the relative humidities are the same, because it's so much warmer, it actually contains so much more water, I only have to cool it down to 74 degrees Fahrenheit. So that means that in absolute terms, since warmer air can hold more water, this parcel of air with a dew point of 74 actually contains more physical water vapor than this parcel of air, even though the relative humidity is 50%. So this is kind of what that looks like, right? Here's a parcel of air with 95% relative humidity. Here's a parcel of air with 10% relative humidity. I'm going to have to cool this one down way less than I'm going to have to cool this one down to achieve 100% relative humidity. Oops. And I'm going to walk you through this tomorrow on the board. The main thing, you don't need to worry about all the math, just the idea, the concept. So this is why actually using relative humidity makes no sense if you're trying to explain how humid it is outside. What you're really trying to decide is how does it feel. So we pay attention to the dew point and the relative humidity. So I would advise you, I would urge you, I would plead with you to stop looking at the relative humidity and start looking at the dew point. The relative humidity doesn't tell you how much physical water is in the air. So this is a handy little chart. If it's like less than 55, it's pleasant. If it's between 56 and 60, it's maybe comfortable. The higher you go in dew point, the worse and worse it feels to your body, because the more and more actual physical water vapor is in the air. Because warm air, again, can hold more water vapor. Here's a similar ranking of the dew points, but based on how your hair is going to look. So lower than 50, it'll be sleek, 55 wavy, 60 curly, 65 frizzy, and 70 just put in a ponytail because it's too humid. So this all ties into climate change because the fact that warm air holds more water vapor than cold air is crucial. And it explains why, for example, Hurricane Harvey, a major hurricane in the Gulf of Mexico from two summers ago, dumped almost 50 inches of rain on the city of Houston. Without climate change, that hurricane, the same dynamics that created that hurricane, may have dumped significantly less rain because the air is warmer, which means that it can hold more water vapor, which means it eventually can form larger clouds, rainier clouds, etc. Right? So let's look at the graph of all of this. So on this axis, we've got the temperature in degrees Celsius. Okay, so 0 degrees Celsius is freezing. And on this axis, we have the vapor pressure. So here, instead of measuring it as grams per kilogram, we're measuring it in terms of millibars. And the reason we do that is because it's just standardized. We know that at the surface, the whole pressure of the atmosphere is about 1,000 millibars. And so we can very easily use these numbers to then calculate how much water vapor there actually is in the atmosphere. So we're going to refer to water vapor here as millibars instead of grams. It's okay, they're the same thing. Or they're not the same thing, but they mean kind of the same idea. So this red line then represents the saturation vapor pressure line. Meaning, on this XY graph, let's start at 0. At air temperature of 0, I go up to this line, and then I go over, and it's about 5 millibars, which means that 0 degrees Celsius air can hold a maximum of 5 millibars of water vapor. Now we know that as the air gets warmer, it can hold significantly more water vapor. And the relationship is actually modeled by this red line and a set of equations called the Claudius-Clapeyron equations. It's exponential, right? So at 40 degrees Celsius, right? So here, 40 degrees Celsius, the saturation vapor pressure is about 70 millibars. So at 0, it was 5, and at 40, it's 70, which means that 40 degrees Celsius air, or about 100 degrees Fahrenheit, can hold, 14 times as much water vapor maximum as 0 degrees Celsius air. Now, if I go out there with my weather machine and I measure in the atmosphere how much water vapor there actually is, not the hypothetical maximum amount, but just how much there actually is. If it's anywhere in this area here, right, below the saturation vapor pressure line, we call that air undersaturated. It's undersaturated, which means that we can continue to add more water to it, right, water vapor, until it becomes saturated. If it's above this, it's supersaturated. That doesn't really happen all that much in our atmosphere, but I'll explain tomorrow on the Zoom when it actually can happen and what that looks like. So when air parcels are saturated, meaning they contain as much water vapor as they possibly can hold, what happens? Any additional water vapor, right, anything above this line is going to immediately condense, which means instead of a vapor, it's going to exist as a liquid. And if you get a lot of liquid water in the air, you form a cloud. That's what a cloud is. It's a collection of liquid water droplets resulting from saturated air that started to condense. Oops. So let's say we've got this parcel of air here. Okay, it's 30 degrees Celsius, and we went out and we measured, and it has 10 millibars of water vapor. We took that measurement with our weather machine. So that parcel of air is undersaturated. If we want this air to become saturated, okay, we want this parcel of air to be on this line, what can we do? We can either add water vapor or we can subtract the temperature. We can decrease the temperature. So it's very difficult in our atmosphere to add water vapor, but we can decrease the temperature. And the way we decrease the temperature, as I explained in the last video, as I go up in the troposphere, the temperature decreases. So what I can do is I can take that parcel of air and I can move it up. And as I move it up, it cools off and then it can condense. The air can condense. So I can't really add water vapor, that's very complicated, but I can condense this parcel. So, I can decrease the temperature of this parcel, which will lead to condensation. So I'm here, it's 30 degrees, 10 millibars. I need to decrease the temperature. So let's say I decrease the temperature to 20 degrees. So the dot's now here, okay? Still 10 millibars of water vapor. I'm not adding water vapor to it. So the dot's here, still undersaturated. I can decrease it another 10 degrees, and now the dot looks like it's right on the line, which means that it is now saturated, right? So what temperature is this? This is 10 degrees Celsius. At 10 degrees Celsius, this parcel of air, with these measurements that I made in the atmosphere, will become saturated. When it becomes saturated, water starts condensing. Okay, it can no longer exist as a gas, it must condense, and then we can form a cloud. So this is what I was just saying, right? We can either, in order to saturate this parcel of air, we can either add water vapor or we can decrease the temperature. And this is exactly what happens in the atmosphere, right? So here's an example of a parcel of air that's undersaturated. Its temperature is higher than its dew point. Remember, the dew point is the saturation temperature, right? So for example, for this parcel, the dew point was 10 degrees. So for this parcel, the dew point we measure is 65 degrees. So as I go up in the atmosphere, when it finally gets to 65 degrees, a cloud will start to form in that parcel of air. I'm actually going to skip this slide. It's a bit confusing, and I'm going to explain this better when we're live. So we know a couple things about the atmosphere. I mentioned to you that in the troposphere, the temperature decreases as you go up. We know exactly how much it decreases, actually. It decreases according to the dry adiabatic lapse rate. If the atmosphere is dry, meaning that it's not saturated, then every kilometer that we rise, we drop the temperature 10 degrees Celsius. So for every kilometer, we drop the temperature 10 degrees Celsius. Okay? So for this parcel of air at 30 degrees Celsius at the surface, we go up 1 kilometer, it's 20 degrees Celsius. We go up 2 kilometers, it's 10 degrees Celsius. We go up 3 kilometers, it's 0 degrees Celsius, and a cloud starts to form, meaning that 0 degrees is the dew point for this parcel of air. And we know, so if we know the dew point, then we know where the cloud is going to form, because we can use the dry adiabatic lapse rate, right? If we know where the cloud is forming, then we can backtrace and figure out what the dew point is. Now, once there's a cloud, as that parcel keeps rising, the air temperature is no longer decreasing according to the dry adiabatic lapse rate, because that air is now saturated, so it will actually decrease at the saturated adiabatic lapse rate, which is about 5 degrees Celsius per kilometer. And that's because the process of condensation actually gives off heat to the surrounding atmosphere. And I think that was in the first lecture. So the process of condensation actually warms the atmosphere around it. So once you're condensing water in a saturated air parcel, you're going to start warming some of the air around it. So for example, in this figure, I want you to write your answers down. Where does the rising air in this photo reach its dew point temperature? Is it A, is it B, or is it C? Is it A, is it B, or is it C? Okay, so obviously now we know that in order to form a cloud, you've got to lift air up from the surface until it reaches its dew point temperature and condensation can occur. So how does that actually happen in the world? There's 4 ways, 4 major ways. The first one is convergence lifting. Convergence lifting is when you've got 2 parcels of air moving towards each other for whatever reason. A good example of this is the peninsula of Florida, where you have a sea breeze on either side. The sea breeze pushes the air, and then once the two parcels of air meet, they've got nowhere to go but up. They can't go down into the ground, right? So they go up, and as they go up, they rise, they form a cloud. That's convergence lifting. These two parcels of air just happen to be moving towards each other. Another way that we can form a cloud is through localized convection, which is you have air at the surface, and it starts to get even warm. It's already pretty warm, and it gets even warmer. Warm air starts to rise, and as it rises, it will cool off, right? So I'm taking this air, I'm warming it up, it starts to rise, and then as it rises, it will eventually reach its dew point temperature and form a cloud. That's convection. We have that a lot in the Midwest in the summer. It's like thunderstorms. We also have, or we don't, but one way that you can form clouds through lifting air parcels is orographic lifting. You basically have a physical thing in the way of the air. So the air is moving. Let's say I have my mountain here. This is a mountain. How do I? Whatever. Oh, this way. Okay, so this is a mountain, and I have my parcel of air, and that parcel of air is moving towards the mountain. It can't go into the mountain, so it's going to go up the mountain, and as it goes up, it's going to cool off because it's getting higher and higher in the atmosphere, and eventually will form a cloud. That's orographic lifting. The final one is similar to orographic lifting, except instead of a physical mountain in the way, you just have two air masses that are different densities. So you have a cold air mass, which has one density, and you have a warm air mass, which has another density. When they collide, okay, the warm air is going to slide over the colder air, and as it slides over, it will condense eventually up in the atmosphere, and this is known as frontal lifting, like a warm front or a cold front. We have those a lot in the Midwest as well. This leads to the formation, of course, of clouds. These are some different cloud types. We can talk about these in class. They're just fun names. There's no real science involved in the name. I mean, there's a little bit of science involved in the names, which we can talk about, but it mostly refers to where they are located and how they formed. That's what the names are generally in reference to. There's a fun thing about clouds is that clouds are very good at reflecting solar radiation from the sunlight. And so thicker clouds actually cool down the surface, but thin clouds can actually warm the surface. And we'll talk about this as well as we move forward in the semester and we get to the climate change section. So don't worry about this slide. So clouds obviously rain. That's an important feature of clouds. But not all clouds rain. The only clouds that rain are the ones where there are droplets in that cloud that are large enough to fall out. Okay, so a typical cloud droplet is about this size. Obviously, this is not to scale. This is a condensation nucleus, like a piece of dust or sea salt or something, forming a cloud droplet. A typical raindrop is here, and it would go sort of off the screen in relation to the cloud droplet. So you have to get this cloud droplet to this big-sized rain droplet in order to get the cloud to actually rain. And this is something, if you have questions on this or you want to talk about this, I can also answer your questions on the Zoom. So remember, weather, we've been talking about weather in the atmosphere, right? Weather is the state of the atmosphere at a given time and place. It's the temperature, it's the air pressure, it's the humidity, it's the cloudiness, it's the wind speed and direction. Climate is something entirely different, which we'll talk about when we get to the climate part. So we've talked about the temperature of the atmosphere, we've talked about humidity and clouds and water vapor. So let's now talk about air pressure and wind speed, and then that will kind of tie up our segment on the atmosphere and weather. So what is pressure? Pressure is just a measure of force divided by area. So when we talk about air pressure, I'm sitting here, right, and I'm on the third story of my apartment building. There is air above my head, which extends all the way up, to space. There is a ceiling in the way, but there's a roof in the way, but there's still air pushing down on that, which is pushing down on the air below it. So the air pressure being received on my head is a measure of all of the air above my head. Okay, so we can use pressure to sort of measure how much air is pushing down on my head. So if I go higher up in the atmosphere where there's less air, the pressure is going to be much lower, as we said in the first lecture, right? Down here at the surface, the pressure is much higher because there's a lot more air above my head. Now, in general, that's how it is. But there's these things called weather systems, right? So the atmosphere is like a fluid. So when you go to the lake on a particularly calm day, it's very still. Sometimes the atmosphere is very still. If you go to the lake on a really stormy day, there's waves, there's all kinds of things happening. The atmosphere can also be like that. The atmosphere, being a fluid of gas, can do the same thing. And one thing that it can do is it can kind of wave around like this, right? And so if it's waving around, that means that in some places on the Earth there's going to be more air, and then on some places there's actually going to be less physical air above the surface. So when there's less air, we call that a low pressure, meaning there's low air pressure. There's not as much air above you. Okay? And when there's more air above you, we call that a high pressure, when there's just more air above you. Okay? So the weird thing about this, though, of course, is that in a high pressure system, it's generally assumed that the air is moving down, pushing down kind of on top of you. There's so much air pushing down on top of you. In a low pressure area, the air actually is kind of moving up because there's so little air above you. This air from the sides is trying to fill the space to add more air to that column. And so the air is generally kind of moving in an upward direction. And so to depict the difference in high pressures and low pressures, we use these isobar charts. So these isobar charts just are an indicator of how much air is here in this particular segment that's cut off by the isobars, right? So for example, in this high pressure, the isobar says 1020. 1020 is referring to millibars. So in this green line right here, all the air in here amounts to about 1020 millibars of air measuring above you, right? That's what the air pressure is. This line, where is it? 1020, these are all 1020. Okay, so this line then, where's the 1018 line? Oh my god, I'm in the way. So the 1016 line here, okay, this 1016 line means that the air pressure in this region from the 1020 line to the 1016 line is anywhere between 1016 millibars and 1020 millibars. Maybe it's 1017, maybe it's 1019, whatever. That's what the air pressure is in here. And then between here and here, it's anywhere between 1012 and 1016, etc., etc., etc. So these are just contours that are delineating what the air pressure is in certain regions on the Earth. And we use these to depict high and low pressures and storm systems. So then how do we get from that to wind? Well, wind is influenced by two major things. One, it's influenced by the pressure gradient. So if I've got a high pressure over here and a low pressure over here, the air from the high pressure is generally going to want to move in the direction of the low pressure. It's going to want to move from high to low. The distance that it moves, or the difference between the high and the low divided by the distance that the air has to go to get between the two, is a measure of the pressure gradient. Okay, it's basically how much the pressure rises or drops per unit distance on the map. So if the high and the low are really far apart, the pressure gradient is going to be fairly low. We can measure the pressure gradient by how far apart the isobars are on our isobar map. So if the isobars are very far apart, then we have a very small pressure gradient, which means the winds are going to be significantly slower, right? The wind speed blowing across that distance is not going to be as fast as places where the isobars are very close together. So where the isobars are very close together, you have a high pressure gradient, right? So you have a big pressure difference over a small distance. Whereas here we have a small pressure difference over a very large distance, right? So the winds will be slow in this region, and they'll be very high where the isobars are really close together. So this is a storm. This is a sunny day. An example of an extremely high pressure gradient scenario is a hurricane. Okay, so if I look at the isobar map, I can see that these isobars around this hurricane Patricia are very close together, which means that the winds in that region are very high. That's why hurricanes have very high winds. Over here, the isobars, these thicker black lines, ignore the wind barbs here, these isobar lines are very far apart, which means that this is a very calm, low wind situation. This is a very turbulent, high wind situation. But pressure gradient is not the only thing that influences the wind. It does influence how fast the wind is blowing, but it doesn't really influence the direction that the wind is blowing. So this is complicated. So let me just try and walk you through it. So in general, air wants to move from high pressure to low pressure. But because the Earth is spinning, there's an apparent force, which is known as the Coriolis force. So because the Earth is spinning, as things move through our atmosphere, they actually don't move from one point to the other. They actually turn slightly to the left of the original trajectory line. So if I'm, to the right. So for you, it would be this way. So if this is the original direction of the wind, for example, or an object, a ball, okay, and the Earth is spinning, the Coriolis force is actually going to pull that direction, the trajectory, in this direction, right? So instead of going from here to here, it's actually going to go from here. So instead of going from here to here, it's actually going to go from here to here, to the right. So it's going to move to the right. Instead of going up, it's going to move to the right. So, actually, the isobars don't just tell us the pressure gradient, they actually tell us the direction of the wind, too. Because if the Coriolis force is strong enough, then eventually the wind is just blowing along the isobar. Instead of blowing from high to low, it's actually blowing along the isobars, between high and low, which is very strange. So around a low pressure system, right? Around a low pressure system, the wind blows counterclockwise. So it's going to blow counterclockwise. Around a high pressure system, the wind is going to blow clockwise. And you know the direction that it will be blowing because of the isobars. So for example, here, a low pressure system, the wind is blowing counterclockwise along the isobars. On the high pressure system, the wind is blowing clockwise, and you can line it up and you can actually make a pressure map, which we're going to do in our group work today. So I'm sure you have a bazillion questions because this is definitely the most complicated lecture. So write them all down, and we will absolutely get to them tomorrow in the Zoom, for sure.